have discussed what are sequences of real numbers, and we have seen the limits of sequences of real numbers and convergence of sequences of real numbers. We have established some of the results like sequences, converging sequences are bounded, and if the limit exists they are unique, and we have seen some of the other properties of limits as well in limit theorems. Now, analyzing more on what types of sequences are there in real numbers, we can discuss what are called monotone sequences. The first definition being, a sequence xn of real numbers is said to be increasing if x1 is less than or equal to x2 less than or equal to etc. less than or equal to xn and so on. So, we can see that the least element in the sequence is definitely x1, and as n increases, the terms of the sequence also increases. That is why the sequence is said to be an increasing sequence. And a sequence is said to be decreasing on the other hand if x1 is the largest and following terms are lesser and lesser. So, that means as n increases, the terms of the sequence are gradually seems to decrease. So, a set is said to be monotone or a sequence is said to be monotone if it is either increasing or it is decreasing. We can look at some of the examples. We have seen sequence n which is equal to the sequence 1, 2, 3 and so on. We can see that 1 is the least element of the entire sequence, least term, and as we move further and further, the numbers are getting larger and larger, or the terms of the sequence are increasing gradually. Whereas, if we consider the sequence 1 by n on the other hand, we have the first element being 1, then we have 1 by 2, then 1 by 3 and so on. So, that we can see as n is less than n plus 1, the reciprocal 1 by n becomes larger than 1 by n plus 1. So, we can see that as n increases, the terms of the sequence are decreasing. So, this is an example of a monotonic decreasing sequence. This is the notation that we usually use, and this is an example of a monotonic increasing sequence. So, does there exist some sequences which are neither monotonic increasing nor monotonic decreasing? Yes, of course, we can see, for example, negative 1 whole power n, we have discussed this in the previous session, is equal to the set of all elements of the form negative 1, 1, negative 1, 1 and so on. So, it alternates between negative 1 and plus 1 for the entire sequence, and so we cannot say x n is less than x n plus 1, this is not true, and x n is not greater than x n is for every n we cannot say, and this is also not true. So, that means we cannot say that this is a monotonic increasing or a monotonic decreasing sequence. So, there can be some such examples. In some textbooks, we consider the constant sequence also as a monotone sequence, but it is neither an increasing sequence nor a decreasing sequence, or in some other textbooks they are considered to be both increasing and both decreasing, because there is an equality also there. So, constant sequences are also, in one sense, they are monotone. Now, why do we require monotone sequences? Definitely to study its convergence. So, a monotone sequence of real numbers is convergent if and only if it is bounded. And where does that converge to? A monotonic increasing sequence definitely converges to its upper bound or supremum, and a decreasing sequence converges to its infimum or lower bound. So, let us see the proof of this result. We have to prove that a monotonic sequence is convergent if and only if it is bounded. So, first we assume that the proof is like this. First, assume a sequence xn which is monotonic, increasing or decreasing, whatever it be, and let this be convergent, is convergent. So, we have studied in the previous session that a convergent sequence of real numbers is always bounded. So, whether it is monotone or not, that does not matter. Every convergent sequence is bounded implies this sequence xn is also bounded. So, one side of the proof is over. That means, if a sequence xn is monotonic and convergent, it is definitely bounded. Conversely, we are going to assume that the sequence xn, which is a monotone sequence and is bounded. So, without laws of generality, let us assume that the sequence xn is monotonic increasing. Without laws of generality, we assume that. And given that this sequence is bounded, therefore, as considering the sequence xn as a subset of R, subset of the set of all real numbers, this is bounded means by the supremum property of R, there exists a supremum, say U, for sequence xn. This is ensured by the supremum property of real numbers. So, what does this mean? Every xn is less than or equal to U, and hence U minus epsilon cannot be an upper bound. This cannot be an upper bound. Why? Because U minus epsilon is less than U, and by our assumption U is the supremum of S, which means it is the least upper bound. So, U minus epsilon cannot be an upper bound of sequence xn. Therefore, there exists some xk such that xk is less than U minus epsilon, greater than U minus epsilon. It is not less than, it should be greater than U minus epsilon, because U minus epsilon cannot be an upper bound of sequence xn. So, xk is greater than U minus epsilon, we got a result. Name it as inequality number 1. Also given the sequence xn is a monotonic increasing sequence. So, what does a monotonic increasing sequence mean? If we have xk to be greater than U minus epsilon, xk to be greater than U minus epsilon, we have xk plus 1, which is definitely greater than xk because our xn is monotonic increasing. So, xk plus 1 is definitely greater than xk, Why? Because of the monotonic increasing sequence. We have xk plus 1 is greater than u minus epsilon, and all the successive terms, that means xk plus 2, xk plus 3 etc., all of them will be greater than u minus epsilon. So, in effect what do we have? Xn is greater than u minus epsilon for every n greater than or equal to k. So, we have established this result, and definitely since u is the supremum of sequence xn, we have xn is less than or equal to u, which is less than u plus epsilon as well for every n. So, this holds for every n. So, combining these two results, that is, we have an inequality number 2 here and inequality number 3 on this side. So, from 2 and 3 combines to give u minus epsilon less than xn less than u plus epsilon for every n greater than or equal to k. Or in other words, subtracting u from each of the terms, what do we get? Negative epsilon is less than xn minus u is less than epsilon for every n greater than or equal to k. And what does this indicate? We have seen in a previous class that if you have minus c less than or equal to a less than or equal to c, that is equivalent to writing modulus of a is less than or equal to c. So, using that notation here, we can write this as modulus of xn minus u less than epsilon for every n greater than or equal to k, and we remember this definition is exactly the definition of converging sequence. So, we have established that given an epsilon greater than 0, there exists some natural number k such that modulus of xn minus u is less than epsilon, and that is why we told that the sequence xn, which is a monotonic increasing sequence, is converging to the supremum. Similarly, if we take a monotonic decreasing sequence, we can show in a similar pattern that this sequence is converging to the infimum as well. That is exactly what we required to prove in the monotone convergence theorem. A monotone sequence xn of real numbers is convergent if and only if it is bounded, and an increasing sequence converges to its supremum and decreasing sequence to its infimum. So, that is the proof of monotone convergence theorem. The next we have a problem. Show that limit of 1 by square root of n equal to 0. So, we have seen such questions in the previous session as well to find the limit of a sequence, but here we are going to use the monotone convergence theorem to show that limit of this sequence 1 by root n is equal to 0. Let us see how we can proceed. To show that limit of 1 by root n is equal to 0. So, by applying monotone convergence theorem, we are going to prove this result. So, first we have to establish that the given sequence xn is equal to 1 by root n is monotone, and see whether it is monotonic increasing or decreasing, and then accordingly we have to find the supremum or the infimum, and then we can conclude limit of this is equal to this. So, consider n greater than or equal to m, where n and m are natural numbers. So, for example, we can take n and n plus 1, so that it is easy for us to understand. Suppose you take n and n plus 1 belonging to n. We know n is less than n plus 1. Therefore, square root of n is less than square root of n plus 1. And since root n is less than root n plus 1, taking the reciprocals, what do we have? 1 by root n is greater than 1 by square root of n plus 1. So, we have 1 by root n is greater than 1 by root of n plus 1. So, we can see in general, if n is greater than or equal to m, 1 by root n is less than or equal to 1 by root m, because as the denominator increases, the reciprocal is, or the term is decreasing. So, we can see that this is a decreasing sequence. Therefore, sequence 1 by root n is a monotonic decreasing sequence. Now, which is the infimum, or if it is monotonic decreasing, we have to show that it is bounded. Then only we can show that it is convergent. So, now the second question arises, whether sequence 1 by root n is bounded. So, if you consider the sequence 1 by root n, this is equal to the sequence of elements 1, 1 by root 2, 1 by root 3 and so on, and finally as n approaches infinity, we can see that this is equal to, the lower bound is nothing but 0. Definitely every element of this is greater than 0. So, 1 by root n is greater than 0 for every n belonging to the set of all natural numbers. So, obviously a question may arise in your mind, square root of n can have both positive as well as negative values. So, in this case, in the case of sequence, we have only, it is a one-to-one correspondence with the set of all natural numbers. So, either it will be completely positive or it will be completely negative. Otherwise, square root functions cannot be considered as functions. So, if we are taking a function or taking a square root in the viewpoint of a function, we by default consider it as a positive square root. So, root n is always greater than 0 for every n belonging to n, and therefore, we can have every element is larger than 0. Therefore, sequence 1 by root n is bounded. So, definitely a monotonic decreasing sequence which is bounded has to be convergent by the monotone convergence theorem. Therefore, applying monotone convergence theorem, by monotone convergence theorem, sequence 1 by n, 1 by root n is convergent. Now, it remains to show that limit of 1 by root n is equal to 0. So, that is enough if you show that the infimum of 1 by root n is equal to 0, and this part we have already discussed in one of the previous sessions, and so we can show that the infimum of 1 by root n is equal to 0 by using the epsilon and epsilon greater than 0 and Archimedean property. We can show that this is equal to 0, and so infimum of 1 by root n is equal to 0 shows that limit of 1 by root n is equal to 0. So, that completes the proof of the first question. that is limit of 1 by root n is equal to 0. The next question is, we are given a sequence xn which is recursively or inductively defined by x1 is equal to 1 and xn plus 1 is equal to 1 by 4 into 2 xn plus 3 for n greater than or equal to 1. We are asked to show that the limit of this sequence is equal to 3 by 2. So, we are given a recursive definition. Let us look at the proof or look at the solution part. We are given x1 is equal to 1 and we are given a recursive definition xn plus 1 is equal to 1 by 4 into 2 xn plus 3. So, xn plus 1 is equal to 1 by 4 into 2 xn plus 3. We are asked to show that limit of this sequence is equal to 3 by 2. So, first we will claim that all these terms in the sequence are bounded by the number 2, because the limit is equal to, how did we get that number 2 is because you have to look at the limit given and you have to look at the first value of x. So, x1 is given to be 1 and limit is given to be 3 by 2 and definitely 3 by 2 is a number which is less than 2, and so we claim that suppose every number is less than 2, is it correct? We are going to claim this. So, for every n. So, definitely this is depending upon n, the set of all natural numbers. So, the proof will be by mathematical induction, proof by mathematical induction. So, let us consider the case x for n equal to 1. So, x1 is given to be 1 which is definitely 2. So, this is correct. Assume xk is less than 2. Then what happens to xk plus 1? Therefore, xk plus 1 is equal to, by the recursive definition, xk plus 1 takes the value 1 by 4 into 2 xk plus 3, and since xk is given to be, since xk is given to be less than 2, we can replace this xk using an inequality 1 by 4 into 2 into 2 plus 3, and that is nothing but 7 by 4. So, we have xk plus 1 to be less than 7 by 4 and 7 by 4 is strictly less than 2. Therefore, we have xk plus 1 is also less than 2, which indicates that xn is less than 2 for every n by the principle of mathematical induction. So, the first claim is proved. So, we have an upper bound here. We have every xn is bounded above by 2, and then applying the monotone convergence theorem, we have to show that it is a monotonic increasing sequence, so that the monotonic increasing sequence converges to the supremum. So, this is an upper bound, this is 2 is an upper bound. So, if we are succeeding in showing that this is a monotonic increasing sequence, then definitely it will be convergent. So, let us see whether it is monotonic increasing. So, the next claim, claim 2 is that the sequence xn is monotonic increasing. Again, we apply the induction here. We have x2 is equal to, what was x2? x1 is given to be 1. So, you have to apply n equal to 1 in this definition. So, what is x2 actually? x2 will be 1 by 4 into 2 into 1 plus 3, that is equal to 5 by 4. So, we are having x2 is equal to 5 by 4 and x1 is equal to 1, x2 is equal to 5 by 4, x1 is equal to 1. So, 5 by 4 is strictly greater than x1. So, this is greater. So, the induction hypothesis, the first value for n equal to 1, it is true. Now, consider the case when n equal to k. That means, we assume that xk plus 1 is greater than xk. Then consider xk plus 2, which is equal to 1 by 4 into 2xk plus 1 plus 3, that was the definition. 1 by 4 into 2xn plus 3. So, 1 by 4 into 2xk plus 1 plus 3, that is strictly greater than 1 by 4 into 2xk plus 3, and what is this value? This is equal to xk plus 1. So, having assumed the result is true for n equal to k, we have now proved that the result is true for n equal to k plus 1. Therefore, we have xn is monotonic increasing for every n. For every n. Hence, we have sequence xn to be monotonic increasing and bounded, and therefore, by monotone convergence theorem, sequence xn is convergent. And we were given an inductive definition or recursive definition, xn plus 1 is equal to 1 by 4 into 2xn plus 3, and now we have proved that because the sequence xn is monotonic increasing and bounded, definitely by monotone convergence theorem it is convergent, and let x be the limit of this sequence xn. So, as n approaches infinity, xn is approaching x. So, as n approaches infinity, the left side also approaches x, whereas the right side approaches 1 by 4 into 2x plus 3, and solving this, what we have is 4x is equal to 2x plus 3, or in other words, x is equal to 3 by 2. So, this is how we show that the limiting value is equal to 3 by 2. So, that is how we prove the next result. This is equal to 3 by 2. Now, the same technique can be used for constructing a sequence xn which converges to square root of a for any real number a greater than 0. So, for example, we have seen square root of 2 is not an rational number, it is an irrational number. We have seen the square root of 2 is how a real number x is equal to square root of 2, or we have seen the existence of square root of 2, and now in this method we can construct a sequence xn using the monotone convergence theorem and show that it converges to square root of a for any real number a greater than 0. So, that is the importance of monotone convergence theorem. And we have discussed monotone sequences, and we have seen monotone convergence theorem, and we have established how an increasing sequence converges to the supremum and how a decreasing sequence converges to the infimum. Thank you.